In 2018, researchers calculated that if every satellite operator on Earth suddenly lost the ability to command avoidance maneuvers, every uplink gone, every thruster command dead, the orbital environment above us would survive statistically intact for about 121 days. 4 months. Enough time to notice, enough time to scramble, enough time maybe to fix it. That number just got updated. As of June 2025, it stands at 2.8 days, a long weekend, Friday afternoon to Monday morning. That's your margin. That's the entire buffer between normal operations and a catastrophic chain reaction collision, and it fell from 4 months to a long weekend in less than 7 years. Now. In 1978, a NASA physicist named Donald Kessler published a paper describing exactly the nightmare that produces a number like that. A scenario where orbital debris gets dense enough that collisions become self-sustaining, each one creating the conditions for the next and the next and the next, until entire orbital bands become permanently unusable. For almost 50 years, the scientific community treated that paper as a warning about the future, something to watch for, something to prevent. Kessler just published an update, and the headline is not what anyone was hoping to read. The threshold he described in 1978 has already been crossed. Not in theory, not on a trajectory, already crossed. Tonight we're going to talk about what that actually means, and more importantly, what it would take to push a system that's already past the tipping point into something we genuinely cannot recover from. Stick around, because the answer is scarier than you'd expect. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss a single update. As this story develops, tell me in the comments where you're watching from, and tell me this. The orbital safety margin above your head collapsed by 97% in 7 years, while tens of thousands of satellites went up, and the whole world called it progress. So did we build the most impressive infrastructure in human history, or did we build the most impressive house of cards? Leave that in the comments, let's get into it. Part 1. The 2.8-day problem. There is a clock running above your head right now. You can't see it, you can't hear it, and until about 6 months ago, almost nobody outside a few specialised research groups had even heard of it. But it exists. It's ticking, and in the last 7 years it has gone from a comfortable buffer of roughly 121 days down to 2.8. 2.8 days, a long weekend, the time between a Friday afternoon and a Monday morning. That is how much margin we now have, according to a new analysis from Dr. Sarah Thiele and her research team, before the low Earth orbital environment would spiral into catastrophic collision if the operators of the world's satellite fleet suddenly lost the ability to command avoidance maneuvers. In 2018, that same clock stood at 121 days. Today, as of the latest June 2025 measurement, it reads 2.8. And if you're wondering whether that kind of collapse represents a smooth decline or something stranger, something more abrupt, you're asking exactly the right question. Because what Thiele's team is describing isn't a trend, it's a phase transition. The kind of thing that happens to water when it freezes, or to a forest when the humidity drops just low enough for the first spark to matter. One moment the system is stable, the next it isn't, and nothing in between looks all that different until you're already on the wrong side of it. Thiele herself uses a phrase that I can't stop thinking about. She calls low Earth orbit a house of cards, not a machine, not an infrastructure, a house of cards. And if you've ever built one as a kid, you already understand why that framing lands so hard. A house of cards doesn't fail because you hit it with a hammer. It fails because somebody sneezed in the next room. It fails because the air conditioner kicked on. It fails because of the smallest, most unremarkable disturbance you can imagine, and then it fails all at once, not gradually, not politely, not with any warning you could act on. The entire structure exists in a state of conditional stability, held up by nothing but the absence of disturbance. And that, Thiele argues, is exactly where we are right now above your head. The old assumptions that defined the first 50 years of the space age, the assumption that orbit was big enough and empty enough to absorb almost anything we threw into it, the assumption that atmospheric drag would quietly clean up after us, the assumption that collisions were mathematical abstractions rather than scheduling conflicts, all of those assumptions belong to a different era. They belong to an orbit that doesn't exist anymore. Let me explain what the crash clock actually measures, because this is where it gets uncomfortable. It is not a prediction of when the next collision will happen. It is not a forecast. It is not a probability model in the usual sense. What it measures is something much more unsettling. It asks a very simple hypothetical question. If, right now, every satellite operator on Earth lost the ability to issue avoidance commands, how long before the first catastrophic collision would statistically occur? How long would the orbital environment survive on its own, without human intervention, before something hit something else hard enough to start a chain reaction? In 2018, the answer was 4 months. You could take the entire global satellite operations community offline for a third of a year, and nothing catastrophic would necessarily happen. Today, that window has shrunk to less than 3 days, and here is the part that should make your stomach drop. Loss of maneuver authority isn't some hypothetical worst case nobody takes seriously. It is the stress test that engineers design their entire operational philosophy around, because it is the scenario that accidentally describes everything that could actually go wrong. A solar storm that knocks out command uplinks, a major cyber attack on a constellation operator, a cascading software error that propagates across a fleet before anyone notices, a bankruptcy, a sanctions regime that strands ground stations. Any of these, any single one, looks from the orbital environment's perspective like the exact same thing. The satellites stop responding, and when the satellites stop responding, that 2.8-day clock starts running. Not hypothetically, actually. What makes this worse, what makes this truly strange, is the exponential sensitivity of the system. A small change in orbital density doesn't produce a small change in risk. It produces a disproportionately large one because risk scales with the square of the object population, not with the population itself. Double the satellites, and you roughly quadruple the conjunction events. Triple them, and you're looking at 9 times the crosschecks, 9 times the near misses, 9 times the decision points where something has to be moved out of the way of something else. The orbital environment is not a linear system. It is a system where every new participant makes the environment harder for every existing participant, and the math gets unforgiving very quickly, which means what you're looking at when you look up at the night sky and see those bright dotted chains of Starlink satellites crossing overhead is not really a network of passive objects drifting in freefall. It is a system that only functions because it is being continuously steered. Every satellite up there is engaged in an ongoing conversation with the ground, being told when to fire its thrusters, when to duck, when to climb, when to hold position, when to dodge. Take that conversation away, even briefly, and the whole thing starts coming apart faster than anyone can respond to. If satellites stop responding, we don't have months, we have a long weekend. So the question that pulls this entire story forward is a brutally simple one. How did orbital safety collapse this fast from 4 months of margin to under 3 days, in less than a decade? And more importantly, what is the man who warned us about all of this almost 50 years ago saying right now? Because Donald Kessler, the physicist whose name is literally attached to the nightmare scenario everyone in this field has been trying to prevent since 1978, has just published an update. And the headline of that update is not what anyone was hoping to read. Part 2, the update that should have been front page news. Donald Kessler worked at NASA for most of his career, and in 1978 he co-authored a paper that most of the public has never read, but almost everyone in orbital mechanics has. In that paper, he laid out a scenario so disturbing it has carried his name ever since: Kessler syndrome. The basic idea is this. If you put enough stuff into orbit around a planet, eventually one of those pieces of stuff will hit another piece of stuff. That collision will produce fragments. Those fragments, moving at orbital velocity, will then hit other objects. Those collisions will produce more fragments. And if the density of objects in orbit is above a certain critical threshold, the process doesn't stop. It feeds itself. Each collision creates the conditions for the next collision, and the next, and the next, until the cascade has generated so much debris that the affected orbital shells become unusable. Not for years, not for decades, for generations. For almost 50 years, Kessler syndrome was treated in most public discussions as a future risk, a thing we might approach, a thing we should be careful about, a thing that might become a problem if we were careless with the space environment. It was the kind of concept that showed up in congressional testimony and insurance actuarial tables and the occasional documentary, always phrased in the conditional tense. Might happen, could happen. On the current trajectory, in the coming decades, we may face. And because it was always framed in that conditional tense, it was also always easy to set aside. Future problem, later problem, someone else's problem. Kessler himself has apparently decided he is done phrasing things that way. In his updated analysis, circulating in research circles over the last several months, and now being taken seriously at every major space agency that has commented on it, his central claim is stark. The runaway threshold he described in 1978 has already been crossed. Not in the distant future, not on some projected trajectory, it has been crossed. Specifically, it has been crossed at the altitudes above roughly 520 kilometers, which happens to be precisely where the largest mega-constellations, including Starlink, operate. 520 kilometers matters because it is, in practical terms, the boundary between an orbital shell that cleans itself and an orbital shell that doesn't. Below that altitude, you still have enough residual atmosphere, thin as it is, to produce meaningful drag on objects. A dead satellite or a piece of debris in a 300-kilometer orbit will re-enter within months or a few years at most, burning up in the atmosphere and removing itself from the risk pool. The environment below 520 kilometers is, in a sense, forgiving. It has a built-in cleaning mechanism. Whatever you put there eventually comes down on its own, whether you want it to or not. Above 520 kilometers, that forgiveness disappears. Drag drops off sharply. Objects persist for decades, for centuries, in some cases effectively forever on human timescales. Whatever you put there stays there. Whatever breaks up there, the fragments stay there. Whatever collides up there, the debris stays there. You are no longer depositing objects into a system that cleans itself. You are filling a container that doesn't empty. And here is the structural irony that makes Kessler's update so disturbing to read. We are deploying mega-constellations into that non-self-cleaning band at the exact moment when the analysis says the runaway threshold in that band has already been passed. We are, in other words, increasing our dependency on the stability of an orbital environment at the exact moment that environment has crossed into a regime where stability is no longer natural. It's like pouring more water into a bucket after the bucket has already cracked, except the crack is invisible, and the water in this case happens to be $10 billion worth of communication infrastructure and critical navigation services that everything from agricultural irrigation systems to airline routing networks depend on. The European Space Agency's Space Environment Report, updated annually and released earlier this year, reinforces this view from an entirely different methodological angle. ESA doesn't use the crash clock metric. ESA tracks debris population evolution, conjunction event frequency, and long-term environmental forecasting based on their own independent models. And their conclusions, arrived at through completely different math than Thiel's team or Kessler's update, converge on the same troubling answer. The operational orbital environment has reached a density and complexity where the current growth trajectory is no longer consistent with a stable environment. Something has to give. Either the growth slows dramatically, which it shows no signs of doing, or the environment degrades, which ESA's projections suggest is already beginning to happen measurably in certain altitude bands. What this collectively means, if you step back from the technical details and look at the shape of the thing, is that a conceptual shift has occurred without most of the public noticing. We have spent 50 years treating Kessler syndrome as a future risk to be prevented. Kessler himself is now saying we didn't prevent it. We are in the early phase of it. The cascade has not manifested as a single dramatic event because the operators of the orbital environment, the satellite companies and space agencies and tracking networks that together form the connective tissue of low Earth orbit, are fighting it every single hour of every single day through relentless active intervention. The cascade is being suppressed. It is not absent. It is being held back. Which brings us to the question that is going to structure the rest of this story. If the runaway threshold has been crossed, if the environment is technically in the early phase of a Kessler cascade, what is still holding it back? What is keeping the house of cards standing? And how fragile, really, is that thing that is holding it back? Because the answer to that question is exactly what the crash clock is trying to measure. And the answer, as you already know, is 2.8 days. Before we dig into the mechanism that is holding this whole thing together, though, we need to talk about what happened in November. Because in November 2024, something happened that turned every single one of these abstract concerns into a concrete lived event for 3 human beings trapped in a capsule above the Earth. Part 3. The Shenzhou 20 incident. In November of 2024, the Chinese crewed spacecraft Shenzhou 20, docked at the Tiangong space station, was struck by a piece of orbital debris. The impact damaged one of the spacecraft's windows. The damage was not catastrophic in the sense that the spacecraft did not depressurize. The crew was not immediately harmed, and the station itself remained operational. But the damage was serious enough that the capsule could no longer be trusted for re-entry. 3 taikonauts scheduled to come home suddenly could not come home. Their ride had been broken by something moving fast enough and small enough that nobody saw it coming, and they spent roughly a week stranded in orbit while mission controllers organized an alternate vehicle to retrieve them. The thing to understand about this event is that it was not a micrometeoroid strike, which is the kind of background risk that every crewed spacecraft has always had to accept. A micrometeoroid is a tiny natural fragment, usually dust-sized, travelling through space on its own natural trajectory. They hit things. They have always hit things. Apollo capsules had micrometeoroid impacts. The space shuttle had micrometeoroid impacts. The International Space Station gets hit by them constantly. They are, while not zero risk, the kind of background noise you accept when you go to space. The Shenzhou 20 impact was something different. Early analysis strongly suggests it was a piece of orbital debris, a human-made fragment left over from some previous mission or collision or disposal event, travelling at orbital velocity, carrying with it enough kinetic energy to crack through a spacecraft window and ground a crew. What this event did, more than any statistic or any paper or any agency report, was collapse the distance between theoretical risk and operational reality. The crash clock says we have 2.8 days. Kessler says the threshold has been crossed. ESA says the environment is degrading. And Shenzhou 20 says yes, all of that. And also there are 3 people currently unable to come home because a piece of someone else's old hardware hit their ride. The rescue operation that eventually brought them down was itself a feat of coordination, executed on a timeline that would have been considered remarkable a decade ago, and that, if these events become more frequent, is going to need to become routine in a way that current infrastructure is not really designed to support. And the central thread holds. This is exactly what orbital instability looks like when it stops being a line on a graph and becomes a thing that happens to actual people in an actual capsule on an actual Tuesday. The house of cards didn't collapse, but it shifted, and somebody's window took the hit. Part 4. Debris is reaching the ground. While those taikonauts were waiting for their ride home, pieces of space hardware were doing something else entirely. They were falling out of the sky and landing in fields. In the last 2 years, large fragments of rocket components and deorbited satellites have been recovered, smoking, in cow pastures in Australia, in farmland in Poland, in the scrub outside towns in Argentina. These are not small pieces. These are multi-kilogram chunks of metal that survived atmospheric re-entry and hit the ground at terminal velocity. Nobody, so far, has been killed. Property damage has been minimal, but the frequency is rising, and it is rising in a way that is no longer consistent with the old assumption that re-entering space hardware reliably burns up in the atmosphere. That assumption was never entirely true. It was always a statistical claim, not a physical guarantee. But when you put enough objects up there, and the ones that come down in enough volume, the statistics start producing surface-level events. Aviation risk assessments now project that by 2030, the probability of a commercial aircraft being struck by re-entering debris on any given year could rise to something in the neighbourhood of 2 in 1,000. That number, 2 in 1,000, might sound small, but in aviation risk accounting, where the acceptable risk of catastrophic failure per flight hour is measured in parts per billion, 2 in 1,000 is astronomical. It is the kind of number that, if it materialises, changes the insurance environment, changes routing decisions, changes the economic foundations of how aircraft are allowed to operate in certain corridors. The atmosphere, which we have implicitly treated as a filter for everything we send up, is turning out to be a filter with a capacity limit. And the quiet implication of those fragments showing up in Australian pastures and Polish fields is that the capacity limit is being approached. The leakage from orbit back to the surface is a symptom of the density stress above. The same stress the crash clock is measuring, the same stress Kessler's update is describing, the same stress that cracked the Shenzhou 20 window. Different symptom, same disease. The system is overloaded, and when systems are overloaded, they leak at their edges. Part 5. The illusion of stability. So why doesn't any of this look broken to you? If you walked outside tonight and looked up, you would see satellites, thousands of them, if your eyes are adjusted and the sky is dark enough. You would see those Starlink chains gliding silently across the stars, beautiful in their own eerie way, and you would see no sign whatsoever that anything was wrong. Your GPS works, your weather forecast works, your international phone call goes through, your streaming service streams. The orbital environment, from the perspective of anyone using it, is humming along exactly as it always has, maybe better than it always has, given the expansion of services those mega-constellations provide. This is the illusion of stability, and it is one of the most important things to understand about the current situation. The reason orbit still appears stable is not because it is stable in the way we used to mean that word. It is stable because a staggering, continuous, almost invisible effort is being applied to keep it stable, second by second, hour by hour, day by day. The numbers here are genuinely difficult to process when you see them laid out. Thousands of avoidance maneuvers are commanded every single day across the global satellite fleet. Thousands! That is not per month, that is not per year, that is per day. A conjunction alert, which is the technical term for a predicted close approach between two tracked objects, is issued somewhere on Earth roughly every 22 seconds. Every 22 seconds, somewhere, some tracking system is telling some operator that two objects are going to pass close enough to each other that someone needs to decide whether to do something about it. The infrastructure that makes this possible is a layered dependency stack, and every layer of it has to work or the whole system starts to fail. At the bottom of the stack, you have ground-based radar and optical tracking systems, operated primarily by the United States Space Surveillance Network, but increasingly supplemented by European, Russian, Chinese, and commercial tracking infrastructure. These systems are trying to maintain a continuously updated catalogue of every object in orbit, larger than roughly 10 centimeters. The current catalogue has something like 40,000 tracked objects, with the actual population including smaller debris estimated to be well over 100 million. On top of the tracking layer, you have prediction algorithms, which take those tracked positions and project them forward to identify future close approaches. On top of the prediction layer, you have conjunction screening, which evaluates those predicted approaches and flags the ones that require action. On top of the screening layer, you have the decision layer, where human operators or automated systems choose whether and how to maneuver. And on top of the decision layer, you have the execution layer, where commands are actually sent to spacecraft and those spacecraft actually fire their thrusters. Every single one of those layers has to work. Every single one of them has finite latency, finite accuracy, finite capacity, and every single one of them is under more stress this year than last year, and was under more stress last year than the year before. Conjunction alerts have not grown linearly with the satellite population. They have grown much faster because every new object has to be checked against every existing object, and the number of pairs you have to evaluate scales with the square of the population. Add 10,000 satellites and you don't get 10,000 more cross-checks. You get something closer to 100 million more. The prediction algorithms have to run more often, with more data, and they have to do it under conditions where the underlying uncertainties in orbital position are themselves growing because of factors like variable atmospheric drag, solar activity effects, and the thermal distortion of tracked objects. The decision timelines are compressing because the warning windows for close approaches are compressing. The command uplink networks are more saturated than they used to be. This is what I mean when I say that satellites are no longer passive objects in free fall. They are, functionally speaking, actively piloted infrastructure. A modern Starlink satellite is in almost constant low-level conversation with ground control. It receives conjunction warnings, executes avoidance maneuvers, adjusts its orbit for atmospheric drag, and performs its station-keeping corrections routinely enough that the satellites average something like 41 maneuvers per year, per satellite. Multiply that across the operational fleet, and you are looking at numbers that start to feel less like spaceflight and more like air traffic control at a continental scale, running continuously, without breaks, without weekends, without any tolerance for extended disruption. Which is exactly where the vulnerability lives. Stability in this regime is not a property of the orbital environment. It is a property of the procedure being executed to manage the orbital environment. And procedures, unlike physical laws, can be interrupted. A procedure requires communication networks to function. It requires ground stations to be powered and staffed. It requires prediction algorithms to run correctly on uncorrupted data. It requires the humans and machines making the final decisions to be reachable, responsive, and aligned. Break any of those for any non-trivial length of time, and the procedural stability evaporates. You're left with the underlying physical reality, which is a dense field of high-velocity objects above a crossed cascade threshold, and a crash clock that starts running the moment the procedure stops. So the question the rest of this story keeps circling back to is what, specifically, could break the procedure? And how plausible are those breakage scenarios, really? Because the crash clock is not a measurement of orbital physics, it is a measurement of how long we have if the procedural layer fails, and the procedural layer, whatever its redundancies, is made of networks and humans and software and economic contracts and geopolitical agreements, all of which are nowhere near as robust as people like to believe. Not even close. Let me show you the geometry of the environment we're actually operating in. Part 6. The geometry of catastrophe. Every 22 seconds, somewhere in low Earth orbit, two objects pass close enough to each other that tracking systems flag the event. Every 22 seconds, around the clock, around the year. This is the rhythm of the modern orbital environment, and it is one of those statistics that only becomes terrifying when you sit with it for a moment. Every 22 seconds means, over the course of a single 24-hour day, roughly 3,900 conjunction events globally. Most of them are resolved without action. The objects pass, the predicted missed distance turns out to be acceptable, and life goes on. But every single one of them has to be identified, evaluated, and classified. Every single one of them consumes processing time, analyst attention, bandwidth, decision authority, and every single one of them is a potential false negative, where the system declares an event safe that turns out not to be, or a false positive, where the system calls for an avoidance maneuver that didn't actually need to happen and expends fuel that has to be replaced somehow. The reason conjunction frequency is rising so fast is because risk in a dense orbital environment does not scale linearly with the number of objects. It scales with the number of possible pairs. If you have 10 objects in orbit, you have 45 possible pairs to check. Double to 20 objects, and you have 190 pairs, more than 4 times as many. Go to 100 objects and you have roughly 5,000 pairs. Go to 10,000 objects, which is approximately where we are in active satellites today, and you have about 50 million pairs to continuously evaluate. Add the debris population and the inactive object catalogue, and you're into cross-check counts that require dedicated high-performance computing resources just to keep up with the basic arithmetic. This is what the nonlinear growth of orbital risk looks like in practical terms. Every new satellite doesn't just add one line of risk, it adds a line of risk against every single object already up there, and it does so in both directions. What this nonlinear growth does, eventually, is saturate the prediction systems themselves. And this is where the math starts doing something genuinely unsettling. Tracking positions in orbit has inherent uncertainty. An object's predicted location at a given future time isn't a single point. It's a probability ellipsoid, a region of space within which the object is expected to be with some degree of confidence. Those ellipsoids are larger than people tend to realize, sometimes kilometers across for objects tracked at typical accuracies. When two objects are approaching each other, what the conjunction screening system is actually asking is whether their two uncertainty ellipsoids overlap, and if so, by how much. When the orbital environment was sparse, those uncertainty ellipsoids were usually well separated, and the overlaps that did occur were rare enough to handle individually. As the environment densifies, the ellipsoids start overlapping more often, and the system starts to approach what researchers sometimes call the probabilistic noise floor, where the number of potential conjunction events becomes so large that distinguishing genuine threats from statistical artifacts becomes harder. This produces a specific and particularly insidious form of risk, which is that the system can become accidentally confident in its own safety. If every object pair is flagged as a potential close approach, and most of them resolve without incident, operators can develop a kind of alarm fatigue. A close approach that would have triggered a maneuver 5 years ago gets downgraded because that kind of close approach is now routine. Risk thresholds drift, expectations adjust, and somewhere in that drift, a real high-risk conjunction gets classified the same way as the dozens of low-risk conjunctions being resolved that same hour, and the maneuver that should have happened doesn't. The asymmetry here is brutal. Detection at this density is hard but possible. Prevention at this density is harder, because prevention requires not just correctly identifying risk, but correctly ranking it against a background of continuous noise. What the geometry of the environment is telling us is that low Earth orbit has become what might reasonably be called a continuously near-collision environment. Collisions are not rare events that we occasionally worry about. They're events that are continuously being prevented, continuously averted, continuously worked around by a system running at near its operational limits. The appearance of safety is not the absence of danger, it is the presence of unbroken intervention. Every uneventful day above your head is a day somebody worked very hard to produce, and that somebody is getting more overloaded every year. Which brings us to the single largest source of that overload, and to the organisation that, more than any other, is shaping what low Earth orbit looks like today. Part 7. The mega-constellation singularity. If you had to pick one thing that pushed the crash clock from 121 days down to 2.8, it wouldn't be a single event. It would be a single company's operational tempo. SpaceX's Starlink constellation, which began meaningful deployment in 2019, now comprises the majority of active objects in low Earth orbit. The exact number shifts week to week as new launches and deorbits change the picture, but the aggregate orbital ecosystem currently contains roughly 14,000 active satellites across all operators, and Starlink alone accounts for somewhere north of 7,000 of them. That means a single private company is operating more than half the active satellites in low Earth orbit. The Amazon Kuiper constellation is building up rapidly. The Chinese Guowang and Tianfan constellations are targeting deployments of tens of thousands of satellites each over the coming years. The OneWeb system is operational. A dozen smaller constellations are at various stages of deployment. By the end of this decade, the baseline expectation among most space agencies is that low Earth orbit will host somewhere between 60,000 and 100,000 active satellites if current plans hold. Starlink's operational load gives us a preview of what managing a mega-constellation actually requires. In recent reporting periods, SpaceX has disclosed that its satellites are performing on the order of 800 plus avoidance maneuvers per day across the constellation. 800 plus maneuvers per day. That's one satellite firing its thrusters to dodge something somewhere over the Earth every 100 seconds or so. Averaged across the fleet, each individual Starlink satellite is performing roughly 41 maneuvers per year, which means your average Starlink is dodging something once every 9 days. The constellation has shifted quietly, and without most people noticing, from being a collection of satellites into being a swarm system. And the distinction matters. A satellite is an object that performs a function while incidentally being in orbit. A swarm system is a distributed, continuously reconfiguring, actively coordinated entity, where the motion of every member depends on real-time awareness of the motion of every other member. Operating a swarm at this scale requires a control architecture that is partially centralized and partially distributed, with satellites able to execute certain avoidance decisions autonomously based on onboard sensors, while receiving high-level guidance from ground control. SpaceX has invested heavily in this autonomy, which is genuinely impressive engineering, and has almost certainly improved the system's ability to handle the current operational load. But autonomy at this scale introduces its own category of risk, because an autonomous system is only as good as the software running it and the data it has access to. If the autonomy logic has a flaw, that flaw exists simultaneously on thousands of satellites. If the data feed is corrupted, thousands of satellites are making decisions on corrupted data. The architecture that allows a mega-constellation to function also makes it a single, coupled system in ways that a diverse collection of individually operated satellites would not be. There is a kind of paradox at the heart of all this, and it is the paradox that, more than anything else, keeps showing up in the current round of orbital safety analysis. The more satellites you add to an orbital environment, the more control you need to exert to keep that environment safe. But the more control you need to exert, the more sensitive the environment becomes to the failure of the control layer. 100 satellites can be managed with modest procedural infrastructure. 14,000 satellites require sophisticated, continuous, tightly synchronized coordination. 100,000 satellites, which is the trajectory we are on, will require coordination at a level that stretches the limits of what current organizations and technologies can provide. And at every step along that scaling trajectory, the consequence of a control layer failure gets worse. You are building a taller and taller house of cards while also making the cards more and more interdependent. The system becomes stronger at handling routine traffic and weaker at handling any scenario where the coordination layer itself is the thing that goes wrong, which is the core tension nobody has figured out how to resolve. What if the control layer is the weakest link in the system it is supposed to stabilize? What if the very sophistication that makes mega-constellations viable is also what makes them structurally vulnerable to the kind of disruption that used to be manageable when the environment was simpler? The old space age tolerated ground station outages and command latency because the environment didn't punish you much for those things. The new space age cannot tolerate them because the environment will start cascading while you scramble to restore service. The procedural stability of the system is, in a very real sense, only as good as the reliability of the organizations and networks providing the procedure. And there is nothing in physics that says those organizations and networks will be reliable forever. That's the question looming over everything, and to understand why the altitude those satellites are operating at makes this worse rather than better, we have to talk about that number again. 520 kilometers. Part 8. The 520 kilometer line. Atmospheric density at the altitude of the International Space Station, roughly 400 kilometers, is something like 10 to the negative 12th kilograms per cubic meter. This is a vanishingly small number by any normal standard. For practical purposes, you are in vacuum, but it is not zero. That residual atmospheric density, as tenuous as it is, still exerts measurable drag on objects moving through it at orbital velocity. That drag is what makes the International Space Station require regular reboost maneuvers. It is also what makes that orbital regime self-cleaning on timescales of months to years. An object abandoned at 400 kilometers without station-keeping capability will typically re-enter within a year or two, burn up, and be gone. At 500 kilometers, atmospheric density drops by roughly an order of magnitude. At 600 kilometers, another order of magnitude. At 700, another. This is not a linear relationship. It is an exponential decay, and it means that the orbital persistence time of objects increases with terrifying speed as you move up. 520 kilometers is, roughly, the practical crossover point. Below that altitude, natural orbital decay is fast enough that, for planning purposes, you can assume objects will eventually come down even without intervention. Above that altitude, natural decay is slow enough that objects persist on timescales of decades to centuries. An abandoned satellite at 800 kilometers might remain in orbit for 100 years or more. A debris fragment at 1200 kilometers might remain in orbit for over 1,000 years. Above 1500 kilometers, the numbers become effectively permanent on any human timescale you care to use. Starlink operates primarily at altitudes between roughly 540 and 570 kilometers. Read that again. Those altitudes are above the crossover. Starlink is operating in the persistence band, not the decay band. The altitude choice was not arbitrary, and it wasn't made by people who didn't know about the trade-off. It was made because lower altitudes produce lower communication latency, which is the single largest performance advantage Starlink offers over the geostationary satellite internet systems it is displacing. The physics of signal propagation makes lower orbits faster for round-trip communication. And because latency is the commercial battlefield on which Starlink is competing, the altitude choice reflects a deliberate trade-off between operational latency and orbital safety. The company chose latency. And they made that choice knowing that every satellite they put at those altitudes would, if it ever became uncontrolled, persist in the environment for decades. The unintended consequence of this trade-off, aggregated across the entire mega-constellation ecosystem, is the creation of what you might call a permanent debris shelf. A volume of space that is accumulating objects at a rate that exceeds the rate at which those objects are removed by natural processes. In the altitude band between 500 and 1200 kilometers, the math of accumulation is not complicated. Nothing goes away on its own. Whatever breaks up there, the fragments stay. Whatever collides up there, the debris cloud stays. Whatever is abandoned there, it stays. And because the accumulation is happening into a fixed volume of space, the density is rising in that volume every year, and it will continue to rise even if launches stop entirely tomorrow, because the existing population will take generations to naturally clear. This is the reframing that changes how you think about orbital sustainability. We did not just populate orbit, we filled a container that does not empty. Imagine a bathtub with no drain, and a faucet that has been turned on for decades, and a tendency for the water itself, given enough time, to produce more water through its own internal dynamics. That is the 520-kilometer band today. The self-amplification dynamic is what Kessler's updated analysis is describing. Once the density is high enough, collisions generate debris, debris generates more collisions, and the cascade becomes self-sustaining. The threshold for that self-sustaining behaviour, according to the new numbers, has already been crossed. The only thing keeping the cascade from manifesting is the continuous active management that is propping up the house of cards. And every single day, we add more objects to the container because the commercial pressure to do so is enormous. The regulatory framework to slow it is weak, and the consequences of not doing so are borne by future decades rather than current quarters. The container is filling. It is not empty. And the question is no longer whether we should populate this band. The question is what happens when we eventually have to stop managing it. Part 9. The cascade that doesn't need time. When Donald Kessler first described the cascade syndrome that now bears his name, he imagined it as a slow process. In the 1978 paper, the timescales he projected for meaningful cascade development were measured in decades. The math he was working with assumed relatively sparse debris populations, relatively predictable collision rates, and a long tail of secondary events that would take a long time to build up to operational significance. The policy responses that emerged from that original framing reflected its timescales. We would monitor the environment, we would track the debris. We would have decades to respond if the situation started to develop. The modern analysis, including both Thiele's crash clock work and Kessler's own update, describes something that looks almost nothing like the slow cascade model. In the modern model, the slow cascade is a background process that has been running for years and has now brought the environment to the edge of a fundamentally faster regime. In this faster regime, the cascade isn't a multi-decade process with occasional major fragmentation events. It is a rapid process that, once initiated, progresses on a timescale of days to weeks, and the trigger for entering this faster regime is not a collision, it is the loss of active management. The moment the procedural stability layer goes offline, the environment stops being stabilized, and the cascade dynamics that are currently being suppressed start running at their natural speed. The crash clock is, in effect, an estimate of how fast the natural speed of that cascade currently is, 2.8 days, and the numerical estimate Thiele's team has put on the follow-on dynamics is even more striking. If avoidance authority is lost for 24 hours, the probability of at least one catastrophic collision over the subsequent period rises into the 30% range. Extend the outage to multiple days and the probability climbs further. This is no longer a slow cascade. This is what researchers are beginning to call time-compressed orbital failure. The debris generation events happen at orbital velocities, which is to say they happen almost instantaneously from a human perspective. A collision at 7 or 8 kilometers per second doesn't take minutes, it takes milliseconds. The energy released, the fragment cloud produced, the immediate change in the local debris environment, all of those things are effectively instantaneous, and once they exist, they propagate through the environment at orbital speeds, sweeping through other objects and producing new conjunction geometries on timescales that are, from the perspective of human decision-making, terrifyingly fast. This is the core systemic mismatch that makes the current situation so fragile. Orbital physics operates on physics timescales. Human institutional response operates on human timescales. Those two things used to be in approximate balance, because the environment was sparse enough that physics timescales produced events at roughly the rate human institutions could handle them. That balance has now been broken. Physics is generating potential events at rates that outpace the ability of any plausible institutional response to manage them without continuous, uninterrupted operation of the active management layer. Stop the management for a day, and physics generates more events than the restored management can catch up on. Stop it for a week, and the environment has measurably degraded. Stop it longer and you are in cascade territory. The term I keep coming back to is that time is no longer a buffer. For most of the history of the space age, time was the resource that made orbital management tractable. You had decades to solve problems. You had years to respond to warnings. You had months to coordinate responses. That resource is gone. Time has been compressed to the point where it is now a constraint rather than a resource. The 2.8 days of the crash clock is not a comfortable planning window. It is the structural limit within which any failure mode must be resolved or the system begins to cascade. And 2.8 days, when you think about the kind of disruptions we're talking about, is not very long at all. Part 10. Why one collision is enough. Let me give you 2 historical data points to sit with. In January of 2007, the Chinese government conducted an anti-satellite weapon test against one of its own defunct weather satellites, Fengyun 1C, at an altitude of roughly 865 kilometers. The test was a kinetic intercept, meaning a physical object was flown into the satellite at extremely high relative velocity. The satellite shattered, and it didn't just shatter into a handful of pieces, it generated, by the best current estimates, more than 3,000 trackable debris fragments and tens of thousands of smaller fragments below the tracking threshold. Those fragments are still up there. Almost 20 years later, the Fengyun 1C debris cloud remains one of the largest single contributors to the trackable debris population in low Earth orbit, and it will remain so for decades more. In November of 2021, Russia conducted a similar test against its own defunct Cosmos 1498 satellite, another kinetic intercept, another fragmentation event, another long-lived debris cloud that will persist for decades. The point of these examples is not to relitigate the geopolitics of anti-satellite testing. The point is to illustrate something much simpler. One collision is enough. One fragmentation event produces thousands of long-lived debris fragments. Those fragments circulate through the environment for decades, each one carrying the potential energy to initiate its own fragmentation event when it encounters another object. The Fengyun 1C cloud will, over its operational lifetime, produce some number of secondary conjunctions that contribute to the ongoing conjunction load on the global tracking system. Some fraction of those conjunctions will be close enough to require avoidance maneuvers by operational satellites, and across the thousands of fragments, over decades, the aggregate effect is to permanently elevate the background risk level in the affected altitude bands. This is why the orbital stability question keeps coming back to preventing even single-point failures. The environment has no mechanism to undo a major fragmentation event. You cannot unbreak the debris cloud. You cannot pull the fragments back together. Once the event has happened, the debris is there, and the only question is how long it takes for the environment to clean it up through natural drag processes, which in the persistent altitude bands means decades to centuries. The central thread of this entire story keeps tying back to this. A house of cards that takes decades to reassemble if you knock it over, held up by procedural stability that could be disrupted by any of a dozen plausible events. The asymmetry between how easy it is to break this system and how hard it is to fix is what makes the whole situation so fragile. Which means the stability we are observing right now is fundamentally dependent on nothing going catastrophically wrong, not even once. And when you're dependent on nothing going wrong, the first question you have to ask is what, specifically, could go wrong. So let's walk through the triggers. Part 11. The solar storm scenario. 93 million miles from Earth, there is a star. It is, on most days, a remarkably stable star, which is why life here has been able to develop over billions of years. But the Sun is not entirely stable. It goes through approximately 11-year activity cycles, rotating between periods of relative quiet and periods of intense magnetic activity. And during those active periods, it periodically ejects enormous quantities of plasma and magnetic field into space. These events are called coronal mass ejections, and they are the single largest external threat to the operational orbital environment we have been discussing. When a coronal mass ejection is directed toward Earth, several things happen over the course of the following days. The leading edge of the plasma cloud arrives at Earth somewhere between about 15 hours and 4 days after the eruption, depending on the speed and geometry of the event. When it arrives, the magnetized plasma interacts with Earth's magnetosphere, producing a geomagnetic storm. The storm deposits energy into the upper atmosphere, causing it to heat and expand. That expansion is the critical piece for orbital mechanics. A heated, expanded thermosphere reaches higher altitudes than a cool, contracted thermosphere does, which means objects at a given altitude suddenly find themselves in denser atmosphere than they were before. Denser atmosphere means higher drag. Higher drag means faster orbital decay. Faster orbital decay means every satellite in the affected altitude band is suddenly on a slightly different trajectory than it was before, and every predicted position in the conjunction screening catalogue is suddenly slightly wrong. That would be bad enough on its own, but it's only half of the problem. A major geomagnetic storm also induces electrical currents in conductors and disrupts high-frequency radio propagation. Those induced currents can damage electronics in spacecraft that are not adequately shielded. They can corrupt data transmissions. They can knock ground stations offline. They can interfere with GPS timing signals, which are used not only for position, but as the underlying timing reference for enormous amounts of terrestrial infrastructure. And they can do all of this simultaneously on a global scale, because unlike most terrestrial disasters, which are geographically bounded, a geomagnetic storm affects every satellite in every orbit at roughly the same time, and it affects every ground station in the affected hemispheres at roughly the same time. The historical reference point here is the Carrington event of 1859, when an enormous coronal mass ejection struck the Earth and produced effects severe enough that telegraph systems were disrupted globally, in some cases sparking fires from induced currents in the wires. We have not experienced an event of comparable magnitude since, but we have had close calls. In 2012, a coronal mass ejection of similar projected magnitude to the Carrington event crossed Earth's orbital path, missing the planet by approximately 9 days of orbital travel. If the event had occurred 9 days earlier, it would have struck Earth with consequences that, in the judgment of several space weather researchers, could have been among the most disruptive natural events in modern history. The reason a modern Carrington-scale event is qualitatively different from the 1859 version is that we no longer use telegraphs. We use satellites, we use semiconductors, we use global positioning systems and precision timing networks and electric grid synchronization and financial transaction systems that depend on those timing networks, and every single one of those systems is, to some degree, vulnerable to the kind of disruption that a major coronal mass ejection can produce. And when you look at where satellite vulnerability intersects with orbital stability, the picture gets worse. A major solar event would simultaneously disrupt the tracking systems that produce conjunction predictions, the command networks that send avoidance maneuvers to satellites, and the satellites themselves, some of which might be damaged badly enough by induced currents or charged particle exposure that they lose the ability to respond to commands even if the commands got through. You could, in a single event, lose portions of the tracking layer, portions of the command layer, and portions of the execution layer all at the same time across the global fleet, for a period ranging from hours to days depending on severity. The procedural stability of the system could be degraded everywhere simultaneously with no geographic redundancy to fall back on. The Sun, in other words, is a universal trigger. It doesn't care about international borders, it doesn't care about corporate boundaries. It affects everything exposed to it at roughly the same moment, and it is, as triggers go, not a rare one. Coronal mass ejections happen regularly. Major ones happen on timescales of years. Carrington-class events happen on timescales of roughly 1 or 2 per century, and we are well inside the window where another one would be expected. The question is not whether a major solar event will stress the orbital environment. The question is when, how severely, and whether the stress lasts longer than 2.8 days. Part 12. The 24-hour window nobody can meet. One thing that might seem to reduce the risk of a solar event is that we can, in principle, see them coming. We have space-based solar observatories, including the Solar and Heliospheric Observatory, and more recently the Parker Solar Probe, that provide continuous monitoring of solar activity. When a coronal mass ejection occurs, we detect it almost immediately. The ejection then takes somewhere between 15 hours and 4 days to reach Earth, which sounds like plenty of time to prepare. The problem is that the time available to prepare is not the same as the time available to act, and the gap between those two things is exactly where the current system runs into trouble. Detecting a solar event gives you an initial rough estimate of its trajectory and arrival time, but the precise characteristics of the event, including whether it will produce a major geomagnetic storm or a moderate one or essentially no storm at all, are not known with any useful precision until it arrives at the monitoring satellites positioned at the first Lagrange point, roughly 1.5 million kilometers upstream of Earth. That provides something like 15 to 30 minutes of high confidence warning before the event reaches Earth. 15 to 30 minutes, not days, minutes. And within that window, what actions, specifically, can the global satellite operations community take to mitigate the impending stress on the orbital environment? The honest answer is that the available actions are limited. Individual satellites can be placed in safe modes, which protects their electronics, but also means they become temporarily non-responsive to maneuver commands. Some satellites can be prepositioned to altitudes where drag variation is less severe, but that prepositioning takes hours to execute and can only be done for a small fraction of the fleet in the available window. Ground stations can prepare for potential communication disruption. Conjunction screening systems can run extra passes of analysis to update their uncertainty estimates. But none of this coordinates cleanly across operators who don't normally share detailed operational information with each other, and none of it addresses the fundamental problem that during the event itself, visibility into the orbital environment will be degraded exactly when the environment needs the most active management. This is the information versus action gap that keeps showing up in space weather preparedness analysis. Knowing that something is coming is not the same as being able to respond to it in a coordinated way. The astrophysics of solar events operates on a timescale of hours to days. The institutional coordination of global satellite operations operates on a timescale of weeks to months, when it operates across operator boundaries at all. Those timescales do not match, and the current architecture of the global satellite community is not designed to bridge them. Imagine trying to coordinate the simultaneous graceful shutdown of the worldwide satellite fleet. Who makes that decision? Under what authority? How is the decision communicated to operators who do not have pre-existing communication relationships with each other? How is compliance verified? How are disputes resolved if one operator believes their satellites should remain active while another believes they should shut down? These questions don't have institutional answers today. They have hopes and best practices and a lot of voluntary coordination that mostly works on normal days and has never been stress tested under conditions that might require a coordinated global fleet response within a few hours. Which means that the worst case scenario for a solar event is not just the physical disruption itself, it is the physical disruption combined with the procedural disruption of trying to respond to it. And the procedural disruption could easily be the longer lasting problem. Physical damage from a solar event might be repairable within days to weeks. Institutional dysfunction in the response leading to a period where the orbital environment operates without reliable active management could easily produce enough follow-on debris generation to materially affect the orbital environment for decades, knowing it is coming, in other words, does not save you. The crash clock is 2.8 days. The institutional response timescale is longer than that. That mismatch alone is sufficient to make the system vulnerable, and it is vulnerable right now. Part 13. The ASAT problem that never went away. The 2007 Chinese anti-satellite test and the 2021 Russian anti-satellite test are both still generating conjunction events in the current orbital environment. Both of those debris clouds are active participants in the orbital environment right now, today, contributing to the daily conjunction alert volume, requiring avoidance maneuvers from operational satellites that cross their paths, and occupying space in the trackable debris catalogue that tracking systems have to continuously monitor. The consequences of those tests did not end when the international diplomatic reactions ended. They did not end when the news cycles moved on. They are ongoing, and they will continue to be ongoing for decades more. This is what I mean when I say the orbital environment retains memory of violence. Every major fragmentation event that has ever occurred at persistent altitudes is, in some meaningful sense, still happening. Its effects are still rippling through the environment. Its debris is still producing secondary conjunction risks, and some fraction of those secondary risks will eventually produce additional collisions, which will produce additional fragmentation, which will persist for additional decades. The geopolitical decisions to conduct those tests were made in moments, over periods of hours or days. The environmental consequences are being paid out across generations, and the geopolitical incentive structure that produced those tests has not gone away. Anti-satellite weapons remain, for military planners in several countries, a conceptually attractive capability. They are a way to threaten or disable the space-based assets of potential adversaries. They are a demonstration of technological capability. They are, in certain strategic framings, a form of deterrence. The international norms against their use are weak, the treaty frameworks are fragmentary, and the likelihood that more tests will be conducted in the coming years is, honestly, higher than most people who think about orbital sustainability are comfortable admitting. Every one of those future tests, if it occurs in a persistent altitude band, will produce a debris cloud that persists for decades. Every one of those debris clouds will contribute to the conjunction load on the already stressed management system, and every one of those clouds will push the crash clock closer to zero. There is also a scarier version of this scenario, which is not a test but a conflict. If major powers ever engaged in an actual shooting war in space, which is not a scenario anyone plans for explicitly, but which is a scenario that sits quietly in the corner of military strategic thinking, in several countries, the debris generation events would not be singular tests. They would be sustained campaigns, possibly involving tens or hundreds of deliberate fragmentations across multiple altitude bands. The orbital environment could transition, in a period of days to weeks, from its current stressed but managed state to an unmanageable cascade state. There is no recovery path from that scenario on any timescale shorter than generations, and some of the affected altitudes would simply become unusable for the foreseeable future of human civilization. This is not science fiction. It is a scenario that is regularly wargamed by defense analysts in several countries, and the results of those wargames are uniformly sobering. The past actions that shape the current orbital environment are still shaping it. The future actions, whether deliberate tests or hypothetical conflicts, would compound the current fragility. And none of the current procedural management, however sophisticated, can substitute for the prevention of intentional fragmentation events at persistent altitudes. The orbital environment, as it currently exists, requires a kind of diplomatic and military restraint that has not historically been a reliable feature of human international relations. The House of Cards depends not just on technological coordination, but on the continuous choice, by every government that has the capability to fragment a satellite at persistent altitudes, not to do so. Part 14. The software failure scenario. Let's talk about a trigger that sounds more boring and is in some ways more unsettling than any of the others. Software. Modern mega-constellations are not operated through manual commands. They're operated through layered software systems that handle conjunction screening, maneuver planning, command uplink, status monitoring, and increasingly, autonomous onboard decision-making. The software stack for a constellation like Starlink is enormous. It includes ground segment systems for orbit determination and prediction, space segment systems that run on the satellites themselves, communication protocols that shuttle data and commands between the two, and networks of automated update systems that push new versions of firmware and software to the fleet on a regular cadence. Every one of those software layers is a potential point of failure, and because modern constellation operations rely heavily on common software stacks across thousands of satellites, a flaw in the software does not manifest as a problem on one satellite, it manifests as a problem on every satellite running that software. This is not a hypothetical concern, it is the standard operating reality of any large-scale software-controlled system. A software update that passed testing but turns out to have a bug in a corner case propagates to the entire fleet before anyone notices the bug exists. A cybersecurity vulnerability that is exploited by a sophisticated attacker can affect thousands of satellites within minutes. A data corruption event in the conjunction screening system can produce incorrect maneuver commands that are executed faithfully by every satellite that receives them. The scenarios that keep space operations professionals awake at night include things like a constellation-wide software update that introduces a subtle error in autonomous avoidance logic, causing satellites to execute maneuvers in the wrong direction, or fail to maneuver when they should. A cyber attack that injects false conjunction warnings into the screening system, causing unnecessary maneuvers that expend fuel and destabilize formations. A ground segment data corruption that sends satellites incorrect orbit determination information, leading to cumulative navigation errors that degrade the accuracy of the entire constellation's predicted positions. A supply chain compromise that introduces a vulnerability into satellite firmware at the manufacturing stage, which then affects every satellite built during that window. None of these scenarios requires a dramatic event. They do not require solar storms or military conflicts or geopolitical crises. They are the ordinary failure modes of complex software systems, applied to a domain where the consequences of ordinary software failures are anything but ordinary. In terrestrial information systems, a software bug that affects a large fleet of devices might cause inconvenience, data loss, service outages. In the orbital environment, the same kind of bug can cause satellites to collide with other satellites, generating debris that will persist for decades and pushing the crash clock closer to its limit. What makes the software failure scenario particularly difficult is that it produces what researchers call cyber-physical coupling risk. The software domain, where errors are cheap to introduce and can propagate at network speeds, is tightly coupled to the physical domain, where the consequences of those errors play out at orbital velocities and cannot be undone. A bug that propagates to 10,000 satellites in 30 seconds can produce physical consequences that take decades to resolve. The asymmetry between the speed of error propagation and the speed of physical consequence is exactly the kind of system design that produces catastrophic outcomes when things go wrong. Low Earth orbit is, increasingly, a software-defined environment. The satellites are the hardware, but their behaviour, their coordination, their safety are all determined by code running on ground systems and onboard computers. And software, as anyone who has ever used a computer knows, is never entirely reliable. It only appears reliable until it doesn't, and when it doesn't do so locally. It does so at the scope of whatever it was controlling, which is, in this case, the majority of the active orbital environment. Part 15. The economic trigger nobody talks about. Here is the trigger that gets almost no attention and might be the likeliest of all of them. Money. Satellites require continuous operational funding. Ground stations require staff. Command uplink networks require bandwidth contracts. Conjunction screening services require software licensing. Every single layer of the procedural stability stack that keeps the orbital environment stable depends on somebody paying for it, continuously, without interruption. And the companies operating the largest fleets of satellites in low Earth orbit are, for the most part, private commercial entities subject to the normal pressures of business cycles, capital markets, competition, regulatory shifts, and the occasional moment where someone looks at the balance sheet and decides the economics no longer work. Most mega-constellation operators are not profitable in any conventional sense. They are operating on investor capital, with business plans that project profitability several years into the future contingent on continued customer growth, stable launch economics, and favourable regulatory environments. Any of those conditions can change. A mega-constellation that loses its financing, or becomes unable to raise the next round of capital, or finds itself in the middle of a corporate restructuring, or simply decides that the unit economics have turned against it, faces a specific and dangerous operational question. What happens to the satellites when the company can no longer afford to operate them? The official answer is that satellites are supposed to be deorbited when their operational life ends. Most modern licensing frameworks require operators to maintain enough fuel to perform an end-of-life maneuver that either brings the satellite down to a lower altitude, where drag will remove it within a reasonable period, or boosts it to a graveyard orbit above operational zones. The unofficial answer, which everyone in the industry knows but rarely says out loud, is that these requirements are inconsistently enforced, frequently inadequately funded, and subject to being quietly abandoned if the company operating the satellites disappears before the end-of-life maneuvers can be executed. A bankrupt satellite company leaves behind what you might call orphan satellites, objects that are still in orbit, still occupying operational space, and no longer being actively managed by anyone. Their station-keeping maneuvers stop happening. Their conjunction avoidance decisions stop happening. They drift, they lose their assigned orbital slots, they become indistinguishable from debris. The insurance markets that underpin commercial satellite operations have their own fragility layer. If claims start rising because conjunctions are producing more actual incidents, or if reinsurance capacity tightens because the underlying risk models stop matching observed loss rates, premiums can spike sharply. If premiums spike sharply enough, some operators become uneconomic. If enough operators become uneconomic, the insurance market for satellite operations can contract to the point where new launches become difficult to underwrite, which constrains the industry, but does not address the problem of the satellites already in orbit, which still need active management regardless of whether the companies operating them are still writing insurance checks. There is a deeper structural issue here, which is that the incentives in the mega-constellation industry are not well aligned with long-term orbital sustainability. A company launching a constellation captures the commercial benefits of that constellation during its operational life, which typically runs 5 to 7 years per satellite. The company is, in principle, responsible for the end-of-life disposal of those satellites. But the company's planning horizon is its own operational life, which is subject to the normal uncertainties of commercial entities. If the company fails or is acquired or restructures, the disposal obligations are among the first things that tend to get renegotiated or abandoned. The debris, meanwhile, persists for decades. The time horizon for environmental consequences is radically longer than the time horizon for commercial decision-making, which is a pattern that should be familiar to anyone who has followed environmental economics in any other domain. Public costs, private benefits, time horizons that don't match. Regulatory gaps make this worse. There is no global enforcement mechanism that can compel a bankrupt Luxembourg-registered operator to execute end-of-life maneuvers on a constellation of thousands of satellites. There is no international fund that can be tapped to actively manage orphaned satellites that are no longer under anyone's commercial control. The current regulatory framework assumes that operators will behave responsibly, and when they don't, the consequences accumulate in the orbital environment without a clear path to resolution. The weakest link in the orbital stability system might not be a solar storm or a software bug or an anti-satellite test. It might be a sequence of balance sheet failures that quietly removes active management from thousands of satellites without producing a dramatic event at all. The crash clock does not care whether the loss of maneuver authority was caused by a geomagnetic storm or a bankruptcy filing. It just starts ticking. Part 16. The two competing realities. Here is what makes the current moment genuinely strange. When you look at the same data that informs all of this analysis, two different and incompatible interpretations are both defensible. In the first interpretation, the orbital environment is a controlled system. Yes, it is complex. Yes, it is stressed. Yes, the crash clock is alarming and the conjunction rates are high and the trajectory is concerning. But the active management layer is working. The thousands of maneuvers per day are happening. The conjunctions are being resolved. The tracking systems are, for the most part, keeping up. The autonomous onboard avoidance systems are improving every year. The industry is aware of the risks and is making meaningful investments in mitigation. From this perspective, the current situation is a challenging operational environment that demands attention and resources, but it is not a crisis. It is a problem being managed. The sky has not fallen. Satellites work. GPS works. The orbital environment is, despite everything, functional. In the second interpretation, the orbital environment is a slow-motion cascade that is already underway. The crash clock is a lagging indicator that has been dropping for a reason. The conjunction rates have been rising faster than the mitigation capabilities. The active management layer is working, yes, but it is working at the limits of what it can sustain, and it is being kept functional by increasingly heroic efforts that are not scalable to the population growth projected over the next decade. The tracking systems are not keeping up with everything, they're only keeping up with the objects large enough to track. The autonomous systems are improving, but not as fast as the fleet is growing. From this perspective, the current situation is not a problem being managed. It is a catastrophe in its early stages that is being temporarily suppressed by procedural interventions that will eventually fail. The sky hasn't fallen because the house of cards is still standing, but it's still a house of cards. The uncomfortable fact is that both interpretations are consistent with the observed data, and the reason they are both consistent with the observed data is that the system is genuinely in an ambiguous state. It sits right at the threshold where it could be either one. The defining feature of phase transitions in physical systems is exactly this kind of ambiguity near the critical point. On one side of the threshold, the system is stable, and any perturbation decays. On the other side, the system is unstable, and any perturbation grows. Right at the threshold, small differences in initial conditions produce dramatically different long-term behavior, and the system's current state does not cleanly tell you which side you're on. There is also a specific observational problem that makes classification harder in real time. The stabilization work happening every day, all those maneuvers and conjunction resolutions, actively masks evidence of underlying instability. If the active management were to stop, we would very quickly learn which interpretation was correct. But we cannot run that experiment without accepting the consequences, which is exactly why the crash clock framing is useful. It asks, in effect, what we would observe if the stabilization stopped, and it derives from that a lower bound on how much underlying instability is currently being suppressed. The answer, 2.8 days, is itself a piece of evidence for the second interpretation, because a stable system would not require stabilization to produce stable behavior over that shorter time window. The researchers in this field describe this ambiguity with a phrase that captures the situation well. We may be in a hidden phase transition, a transition where the system is technically in the new phase, but has not yet manifested the macroscopic consequences of that phase, because the transition dynamics are being actively suppressed. The cascade is happening in the underlying state. The cascade's visible effects are being prevented, and the moment the prevention stops, the visible effects appear. The orbital environment, under this framing, is not stable. It is metastable. It looks stable because the stabilization is working. It is not stable because the stabilization is not optional. The distinction between those two things is exactly the distinction the crash clock is trying to illuminate. Part 17. Why recovery may be impossible. In 2029, if the schedule holds, the European Space Agency plans to launch ClearSpace 1, the first mission in history specifically designed to remove a large object from orbit. The target is a piece of hardware called Vesper, a payload adapter. Left behind from a Vega rocket launch in 2013, drifting in orbit for over a decade, doing nothing useful, contributing to the conjunction load on the tracking systems that manage the broader orbital environment every single day. ClearSpace 1 will rendezvous with Vesper, capture it using a set of articulated robotic arms, and drag it into a controlled atmospheric re-entry where it burns up and is gone. If it works, and the engineering involved is genuinely difficult, it will be a landmark achievement. The first serious operational demonstration that active debris removal is not just a concept, that humanity can actually go up there, grab something, and bring it down. It will also be, in terms of its actual effect on the orbital environment, essentially negligible. Let that sit for a second, because it deserves to. ClearSpace 1 will remove one object, from an orbital environment that currently contains more than 40,000 tracked objects and an estimated population of over 100 million smaller fragments that are too small to track but large enough to be lethal to operational spacecraft. The removal rate that is technically feasible with current debris capture technology, the absolute ceiling of what is possible right now with the best engineering available, is in the single-digit per year range. A few objects per year in optimistic scenarios, maybe a handful more if multiple missions fly simultaneously and everything goes to plan. The generation rate of new debris is orders of magnitude higher than that. Every fragmentation event, whether from a collision, an anti-satellite test, a battery explosion on an old rocket body, or a propellant tank that ruptures years after a mission ends, adds hundreds to thousands of new tracked fragments and tens of thousands of sub-centimeter pieces to the environment instantly. The continued deployment of mega-constellations adds thousands of new objects per year, each of which will eventually reach end of life and, if not successfully deorbited, join the debris population permanently. The arithmetic here is not subtle. It does not require careful interpretation. You cannot remove debris faster than you are adding it, when your removal capability is capped at a few objects per year and your addition rate is running at thousands. The gap between those two numbers is not a rounding error. It is a structural mismatch of such magnitude that no plausible near-term scaling of current removal technology closes it. This is the non-linear cleanup deficit, and it is the reason that active debris removal, despite being the most intuitive-sounding solution to the orbital congestion problem, is far less promising as a strategy than the public imagination tends to assume. The intuition makes sense on the surface. There is too much stuff up there. We should go get it. We have robots. We have rockets. We have articulated arms and deorbit kits, and a ClearSpace 1 mission on the calendar. The intuition is not wrong about the direction. It is wrong about the scale. And in a problem defined by exponential dynamics, being wrong about scale is the same as being wrong about everything. Every serious conceptual design for scaling up debris removal runs into the same cluster of problems, and they compound each other in ways that resist easy engineering solutions. The cost per object removed is high, in the tens to hundreds of millions of dollars range for dedicated capture missions. That cost does not drop dramatically with scale, because the second major problem is that the debris population is not uniform. The objects in orbit vary enormously in size, in tumble rate, in material composition, in geometry, in orbital altitude. A retired communications satellite tumbling slowly at 500 kilometers is a fundamentally different capture problem from a fragmented rocket body spinning at high angular velocity at 800 kilometers, which is a fundamentally different problem from a paint fleck moving at orbital velocity at 200 kilometers. Capture technology that works well on one category of object tends to be useless or actively dangerous when applied to another, which means you cannot build one general-purpose debris collector and run it at scale. You build a custom mission for a specific target at massive cost, and then you do it again for the next target. The political economy surrounding all of this makes it worse. The debris currently in orbit was generated by dozens of different operators across decades of spaceflight. Old Soviet rocket stages, American upper stages from missions flown in the 80s, Chinese anti-satellite test fragments, fragments of fragments from collisions between objects that were already fragments. Establishing financial responsibility for who pays to remove which piece of this accumulated history is a legal and diplomatic problem that has resisted every serious attempt at resolution. There is no international framework that compels any particular actor to fund cleanup of debris they generated. There is no global insurance pool backstopping the cost. There are voluntary guidelines, aspirational frameworks, working groups, and position papers. None of them move debris out of orbit. The high-altitude persistence problem is in a category of its own. Debris at altitudes above roughly 1,000 kilometers will remain in orbit for centuries under natural atmospheric decay, not decades, centuries. To remove objects from those altitudes requires delivering significant propulsive capability to each target, enough delta V to drag something down from a regime where atmospheric drag is essentially zero. Given the number of objects at those altitudes, and the cost and complexity of each retrieval mission, large-scale removal from the persistence band is simply beyond the scalable operational capability of any organisation currently operating on Earth. For all practical planning purposes, the debris at those altitudes is permanent. Permanent on the timescales that matter for any decision being made today, or that will be made in the next several decades. Whatever cleanup technology eventually exists in mature form, and it will exist, eventually in some form, will not be deployed at meaningful scale within the operational lifetime of the infrastructure we currently depend on. The satellites flying today, the constellations being built now, the orbital services that GPS and weather forecasting and disaster monitoring and precision agriculture and financial timing networks depend on right now. In the near term and in the medium term, what is up there is staying up there. That is not pessimism. That is the physics of orbital mechanics combined with the economics of launch and the politics of international space governance, and none of those three things are changing fast enough to matter within the relevant planning window. Which leads to the conclusion that almost nobody in the public conversation around orbital sustainability wants to say out loud, because it forecloses the comfortable assumption that technology will eventually fix this. The only strategy that actually scales, the only intervention available that could in principle stabilize the orbital environment before it degrades past the point of recovery, is prevention. Not cleanup. Not remediation after the fact, prevention. Stopping the accumulation before it compounds further. Specifically, stopping the rate at which new debris is generated from exceeding the rate at which the environment can absorb it through natural decay and the limited active removal that is feasible. Prevention requires things that are harder than engineering. It requires international coordination among governments and commercial operators who have competing interests and no enforceable common framework. It requires regulatory enforcement with actual teeth, applied consistently across jurisdictions that currently have wildly inconsistent standards for end-of-life disposal, conjunction avoidance, and constellation sizing. It requires commercial incentive alignment, some mechanism by which the operators who benefit from launching large constellations also bear the long-term environmental costs of doing so, rather than socializing those costs onto the entire orbital community, and ultimately onto future generations who will inherit whatever orbital environment we leave behind. None of that has been demonstrated, not in the actual behavior of the major actors currently shaping the orbital environment, not in the regulatory frameworks currently governing launches, not in the international negotiations currently underway about space sustainability norms. The growth trajectory of the mega-constellations is continuing. SpaceX's Starlink is expanding. Amazon's Kuiper is building up rapidly. The Chinese Guoang and Tianfan constellations are targeting deployments of tens of thousands of satellites each. the fragmentation risk from all of those objects, from collisions, from end-of-life failures, from the inevitable fraction that become uncontrolled before disposal is complete, is continuing alongside the growth. The procedural management layer being stretched to keep the current environment from cascading is being asked to handle more load every year with no end to that growth in sight. And the long-lived debris from past events, the 2007 anti-satellite test cloud, the 2009 Iridium Cosmos collision fragments, the accumulated failures of 50 years of spaceflight, continues to circulate through the environment, untouchable by any currently feasible cleanup technology, contributing its daily load to the conjunction alert volume and the avoidance maneuver count and the slow compression of the crash clock. The hard implication of all of this is simple, even if it is uncomfortable. If prevention fails, there is no scalable fallback. Cleanup cannot substitute for prevention at any foreseeable level of investment or technological development. The options are not cleanup versus prevention, with cleanup as the safety net if prevention proves too difficult politically. The options are coordinated restraint now, or the loss of large portions of the operational orbital environment for generations. There is no third path. There is no technology coming to the rescue on the timescale that matters. There is only the choice between acting before the threshold becomes irreversible and discovering what irreversible actually looks like. ClearSpace 1 will fly in 2029 if the schedule holds. It will remove Vesper. It will be a genuine achievement. And the orbital environment on the day it succeeds will still contain more than 40,000 tracked objects and 100 million untracked fragments. All of them still up there, all of them still moving at orbital velocity, all of them still requiring the same unbroken procedural management that is the only thing standing between the current fragile stability and something much worse. One object down, 100 million to go, the teaspoon is real, the bathtub is still filling. Part 18. The gyroscope theory of orbit. Picture a spinning top. When you set it spinning, it stands upright against gravity, which ought to pull it over. By every intuition you have about how objects behave, a top balanced on its narrow point should fall. Gravity is pulling it down. Its center of mass is elevated above its contact point. There is no obvious structural reason for it to remain vertical. And yet it does. It stands there, perfectly upright, resisting the pull, holding its position with an almost eerie confidence. The reason is angular momentum. The spin creates a stabilizing force that continuously redirects any tendency to tip, converting what would be a fall into a slow precession, a gentle wobble around the vertical axis that keeps the top from ever actually going down. The top is stable, genuinely, observably, functionally stable. But here is the thing about that stability, and it is the thing that matters for everything we are about to talk about. The stability is not a property of being a top. A top at rest on a table falls over, immediately without hesitation, the moment you set it down without spinning it. The object itself has no inherent tendency to stand upright. The stability is a property of being a spinning top. The rotation is not incidental to the stability. The rotation is not a feature that happens to accompany the stability. The rotation is the stability. They are the same thing. When the spin slows, the stability degrades. When the spin stops, the stability disappears. Not gradually, not after a warning period. The moment the action ceases, the state it was producing ceases with it, and the top falls. Hold that image, because it is the most accurate mental model available for what is currently happening in low Earth orbit, and it reframes the entire question of whether the orbital environment above your head is actually safe. Low Earth orbit, as it currently exists, is not a stable configuration of objects in free fall. That is the intuition most people carry, and it is wrong. The intuition goes something like this. Satellites are in orbit. Orbit is a natural physical state. Objects in orbit stay in orbit unless something pushes them out, and therefore the orbital environment has a kind of natural baseline stability that human management enhances but does not create. In this framing, the management layer, the conjunction screening, the avoidance maneuvers, the tracking networks, the command uplinks, is doing maintenance on a system that would otherwise be mostly fine, keeping things tidy, preventing the occasional close call from becoming an actual collision, adding a margin of safety on top of a foundation that is already reasonably solid. That framing is not just incomplete, it is backwards. Low Earth orbit, as it currently exists in the era of mega-constellations and crossed Kessler thresholds, and a crash clock reading of 2.8 days is a dynamically stabilized system. The stability is being continuously produced by active management, not maintained by it, not improved by it, produced by it. The management is not maintaining the stability. The management is the stability. Take the management away, and the stability does not continue to exist for a while before gradually degrading. It stops existing because it was never a property of the configuration of objects in orbit. It was a property of the ongoing process being applied to that configuration. Stop the process, and the property vanishes with it, immediately, at the speed of orbital mechanics. This distinction between static stability and dynamic stability is not a philosophical nicety. It is the most practically important thing to understand about the current orbital environment, and it completely reorganizes how you should think about the question of whether that environment is safe. In the static stability framing, you ask, is the current configuration of objects safe? Safe meaning, if you left it alone, would bad things happen? And the answer, if you actually left the current orbital environment alone for a few days, is that yes, very bad things would start happening within approximately 2.8 of them. But the question feels weirdly hypothetical, because we are not leaving it alone. We are running the process continuously, the maneuvers are firing, the conjunction alerts are being resolved, the management is happening. So the question of what would occur without management feels academic, and the observed stability of the system, GPS works, satellites stream data, orbital services are delivered, feels like evidence that the system is fundamentally okay, and the management is a prudent enhancement. In the dynamic stability framing, you ask a completely different question. You ask, is the process that is producing the stability robust to disruption? How much stability can the process produce under different conditions? How long can it sustain production under various kinds of stress? What happens in the boundary cases where the process is interrupted, not hypothetically interrupted, but actually interrupted, by a solar storm, by a cyber attack, by a software failure propagating across a constellation, by a bankruptcy that quietly removes command authority from thousands of satellites? These are not hypothetical questions. They are engineering and institutional questions with real, measurable answers, and the answers, when you look at them clearly, are not reassuring. The process is complex. It depends on a layered stack of technical and institutional infrastructure, from ground-based radar tracking networks to prediction algorithms to conjunction screening software to command uplink facilities to the autonomous onboard avoidance systems on the satellites themselves. Every layer of that stack has to function continuously without extended interruption, and the layers are not fully redundant with each other. A failure in the tracking layer degrades the prediction layer, which degrades the screening layer, which degrades the decision layer, which means the maneuvers that should fire don't fire, and the objects that should move don't move. The failure modes cascade downward through the stack faster than institutional response can cascade upward to address them. And those failure modes can be triggered by events that have nothing to do with orbital mechanics. A geomagnetic storm that disrupts radio communications globally, a sophisticated cyber attack targeting a constellation operator's ground segment, a software update that introduces a subtle error in autonomous avoidance logic and propagates to 10,000 satellites before anyone notices the error exists, a corporate bankruptcy that freezes operational decision-making at exactly the wrong moment. None of these triggers are exotic. All of them are plausible on timescales of years, not decades, and any of them, from the orbital environment's perspective, looks like the same thing. The process stops. The spin slows. The top starts to wobble. The process is currently producing 2.8 days worth of stability margin. 2.8 days is the answer to the question of how long the dynamic stability persists if the process generating it is interrupted. And 2.8 days is, by any reasonable assessment, a very thin buffer against disruptions that, in the real world, routinely last longer than that. A major solar event can degrade global communications infrastructure for days. A significant cyber attack on critical infrastructure can take days to weeks to fully remediate. A corporate restructuring or bankruptcy proceeding does not resolve over a weekend. The institutional response timescales for the kinds of disruptions that could interrupt the orbital management process are, in most plausible scenarios, longer than the crash clock. Which means the buffer is not just thin. It is, in a structural sense, insufficient against the class of disruptions it needs to buffer against. The continuous correction requirement is not a feature of the current orbital environment. It is not an engineering choice that could be designed away if we were smarter about it. It is a structural necessity imposed by the physical state of the environment. Satellites at these altitudes must maneuver continuously, not because their operators have chosen to operate them that way, but because the environment does not permit any other behavior if the environment is to remain usable. Active stability is not an enhancement layered on top of passive stability. It is a replacement for passive stability, which the environment no longer possesses. The orbital regime above 520 kilometers, populated with the density it currently has, past the Kessler threshold it has already crossed, is not a regime that has passive stability available as a fallback. There is no fallback, there is only the process, running continuously, producing the stability that the underlying physical configuration cannot provide on its own. And the replacement, the process, the management, the continuous active stabilization is only as good as the networks and institutions and commercial entities and geopolitical agreements that sustain it. Physics is not sustaining it. Orbital mechanics is not sustaining it. Human procedure is sustaining it, and human procedure, unlike physical law, can be interrupted. The orbital environment is still working. This much is true, and it deserves acknowledgement rather than being buried under the weight of everything alarming. The satellites are operational. The services are being delivered, GPS is routing, weather forecasts are running, the conjunction alerts are being issued, the maneuvers are being commanded, the fragments are being tracked, the close approaches are being resolved. The process is succeeding. The spin is continuing, the top is still upright. But the fact that the orbital environment is still working is not the same as the fact that the orbital environment is safe. It is not evidence of underlying stability. It is evidence that the stabilization process is, for the moment, succeeding. Those are different things. Profoundly different things. A patient on continuous life support is still alive. That is true. But alive on life support and healthy are not the same condition, and the distinction matters enormously when you're deciding how much stress the patient can tolerate, how long they can go without the machinery, and what happens if the power flickers. The orbital environment is on life support. The life support is working. The top is still spinning. And for as long as the top is spinning, it looks stable, in the way that spinning tops always look stable, confidently upright, apparently self-sustaining, giving no obvious outward sign of the continuous action required to keep them that way. But you know, because you have watched enough tops, that the stability is an action and not a state, that the moment the action stops, the state does not persist, that the question is never whether a spinning top will eventually fall. The question is only what slows the spin. That is the gyroscope theory of orbit. It is not a metaphor chosen for dramatic effect. It is the most structurally honest description available of what is currently keeping the sky from falling. The sky is not staying up because it is stable. The sky is staying up because someone is spinning the top, and the top right now has 2.8 days left in its spin before the wobble becomes a fall. Part 19. The Controversies and Hidden Narratives. Some of the public conversation around all of this has drifted into territory that deserves acknowledgement before we close. Not because the fringe narratives are worth platforming at length, but because they are actively distorting how people understand the real problem, and the real problem is serious enough that it does not benefit from being dressed up in stories that are easier to tell but harder to defend. So let's go through them, carefully, because getting this right matters more than getting it dramatic. The first framing in circulation is what you might call the billionaires trapped us on Earth narrative. It is emotionally resonant. It has clean villains. It moves well on social media. The argument, stated plainly, is that the current orbital fragility crisis is primarily the fault of Elon Musk and Jeff Bezos, that Starlink and Kuiper represent a kind of privatized vandalism of the commons, that the mega-constellation era was imposed on the orbital environment by the unchecked ambitions of a handful of extraordinarily wealthy individuals, and that if we could only rein those individuals in, the problem would be substantially addressed. There is enough truth in this framing to make it stick. Starlink is, factually, the single largest contributor to the current mega-constellation population. SpaceX's operational tempo is factually straining the active management layer in ways that would not exist at pre-Starlink satellite densities. These are not unfair observations. They are accurate ones. But the framing is analytically incomplete in a way that matters, because it misidentifies the cause and therefore obscures the solution. The underlying physics was going to produce something like the current situation with or without any particular individual operator. The commercial pressure to deploy satellite internet constellations at scale was not invented by Elon Musk. It existed independently of him, driven by the economics of global broadband demand, the falling cost of small satellite manufacturing, the falling cost of launch, and the competitive logic of first-mover advantage in orbital slot capture. If SpaceX had never built Starlink, the trajectory of the technology and the economics made it close to inevitable that some other operator, Amazon, OneWeb, a Chinese state enterprise, a European consortium, would have deployed a large low Earth orbit internet constellation at roughly the same time and at roughly the same scale. The regulatory framework was permissive enough that whoever got there first was going to be able to do it. The orbital environment does not care whether the satellites filling it were launched by a billionaire or a government ministry or a public company trading on a stock exchange. The conjunction mathematics are indifferent to ownership structure. This matters because if you believe the problem is primarily about specific individuals, your instinct is to target those individuals through regulation, through public pressure, through the political mechanisms available for constraining private actors. Some of that is warranted. SpaceX should be held to the highest standards of conjunction avoidance, end-of-life disposal, and constellation sizing transparency. But holding Musk and Bezos accountable, even fully, does not address the structural incentive problem that would have produced this situation regardless of which specific operators led the charge. The problem is systemic. It is a commons problem. It is a regulatory gap problem. It is a mismatch between the timescale of commercial decision-making and the timescale of orbital environmental consequence. Framing it as a villain problem produces the satisfying simplicity of a target and the practical inadequacy of a solution that does not address the underlying structure. The second framing in circulation is more exotic and in some respects more seductive. The claim that the debris environment is not primarily a consequence of commercial deployment, but rather the product of deliberate military programs designing what strategists call orbital denial capabilities. The argument holds that the fragmentation events, the anti-satellite tests, the accumulating debris clouds are not accidents or negligence, but intentional, that certain governments are deliberately cluttering the orbital environment as a form of strategic competition, rendering it unusable for adversaries while accepting the collateral damage to civilian infrastructure as an acceptable cost of geopolitical leverage. This framing has a kernel of truth embedded in it, which is exactly what makes it dangerous. Some governments do think about orbital denial as a military concept. Anti-satellite weapons do exist. They have been tested. The 2007 Chinese test and the 2021 Russian test both produced debris clouds that are still circulating through the environment today, still contributing to the daily conjunction alert volume, and both of those tests were conducted with full knowledge of their environmental consequences. The possibility that some fraction of the orbital stress being experienced right now reflects deliberate strategic behaviour rather than commercial negligence is not zero. It is not a conspiracy theory in the sense of being without any factual basis, but it is wrong as a primary explanation. The tens of thousands of satellites currently populating low Earth orbit are communication satellites, imaging satellites, internet relay satellites, weather observation platforms, and scientific instruments. They are not weapons. They are not designed to create debris. They were launched because there is enormous commercial and strategic value in the services they provide, and because the economics of launch made deploying them at scale financially viable for the first time in history. The main drivers of the current orbital stress are commercial in nature, not military. Attributing the situation primarily to deliberate military intent misreads the commercial logic that is actually driving deployment, and it produces the same analytical error as the billionaire framing from the opposite direction. It gives you a clean story and an inadequate diagnosis, which is worse than a messy story and an accurate one. The third framing is structurally different from the first two, and it deserves more serious engagement because it comes from a more epistemically legitimate place. It is the funding alarmism critique, the argument that researchers working on orbital sustainability are systematically overstating the problem, because overstating the problem secures research funding, generates media attention, and produces the kind of institutional visibility that advances careers and programs. The argument is not that the orbital environment is fine. It is that the specific numbers being cited, the crash clock at 2.8 days, the claims about crossed Kessler thresholds, the projections about cascade timelines, are being presented with more confidence than the underlying models warrant, and that the gap between what the data actually supports and what the public narrative claims is being filled with professional incentives rather than scientific caution. This critique is worth taking seriously as a general epistemic principle. Funding incentives do shape research outputs. Alarming findings do attract more attention than boring ones. There is a real and well-documented tendency in science communication for risk estimates to migrate toward the dramatic end of the uncertainty range as they pass through the translation layers between technical literature and public narrative. Applying that skepticism to orbital sustainability research is not unreasonable. It is in fact the correct epistemic posture to bring to any body of research with significant public policy implications. But the funding alarmism critique runs aground in this specific case on a single powerful fact: the convergence. The findings that define the current picture of orbital stress do not come from a single research group, a single institution, a single funding stream, or a single methodological tradition. Sarah Thiel's crash clock analysis uses a specific modelling approach developed by her team. Donald Kessler's updated threshold assessment draws on decades of independent work in orbital mechanics. The European Space Agency's Space Environment Report uses ESA's own modelling infrastructure, independently developed, independently funded and answerable to a different institutional constituency than any American research group. NASA's Orbital Debris Program Office operates within its own bureaucratic and scientific context. Independent commercial analytics firms, whose incentives run toward accurate risk modelling because their clients make real financial decisions based on their outputs, are arriving at compatible conclusions through entirely different analytical pipelines. When that many independent sources, using different methods, funded by different agencies, operating in different countries with different institutional incentives, all point at roughly the same set of problems with roughly the same level of concern, the probability that the convergence is explained by coordinated funding driven alarmism becomes very small. Convergence of independent sources is one of the strongest signals available in empirical inquiry, precisely because it is hard to fake across institutional and methodological boundaries. The convergence is real. The funding alarmism critique does not survive contact with it. What is actually in dispute in the serious technical literature is something more specific and more honest than any of these framings suggest. The dispute is not about whether the orbital environment is under stress. That is established across all the sources with a consistency that is no longer scientifically contested among people who work on this professionally. The dispute is about timing and about the exact character of the failure modes. Some researchers believe the cascade dynamics will become visibly manifest within a decade. Others believe the active management layer will continue to suppress visible effects for 2 or 3 decades longer. Some believe specific trigger events, a major solar storm, a significant anti-satellite test, a constellation-wide software failure, are imminent enough to warrant treating them as near-term planning scenarios. Others believe the system has more inherent robustness than the crash clock framing suggests, and that the 2.8-day figure, while real, understates the practical resilience of the management layer under stress. These are genuine scientific disagreements, and they matter for policy. A 10-year horizon demands different regulatory responses than a 30-year one. But they are disagreements about when and how, not about whether. The underlying direction is not contested. The orbital environment is under stress. The Kessler threshold has been crossed at operationally critical altitudes. The management layer is being stretched. The crash clock is at 2.8 days and has been falling. These are the agreed facts. The uncertainty is at the edges, not at the centre. The narrative confusion in the public conversation, the billionaire framings and the conspiracy claims and the funding critiques and the contradictory headlines reflects, in part, the genuine uncertainty in the technical community about timing. But it also reflects something else, something that is itself diagnostic. A system near a phase transition looks ambiguous from the outside. It produces conflicting signals. Observers looking at the same data can reach opposite conclusions in good faith, because the data is genuinely consistent with more than one interpretation near the critical threshold. The confusion is not evidence that nothing is wrong. It is evidence that the system is in exactly the kind of state, near a threshold, in an ambiguous zone, generating inconsistent surface signals where confidence is structurally difficult to come by. The confusion is the signal. The fact that nobody can quite agree on how worried to be is itself a precise description of what a system near the edge of a phase transition looks like from the inside, and we are by every serious measure available on the inside. Part 20. The final question. So let's come back to the clock. 2.8 days, that is the current reading. That is how much time the orbital environment would have, according to the best current analysis, between the loss of active management and the first catastrophic collision that could initiate visible cascade dynamics. That number has fallen from 121 days in 2018. That fall has tracked the deployment of mega-constellations, the crossing of the Kessler threshold above 520 kilometers, the increasing density of tracked and untracked debris, and the growing operational complexity of the active management layer. Every trend line that matters for that number has been moving in the same direction. None of the trend lines are showing signs of reversing. The triggers we have walked through are not exotic. They are not the stuff of science fiction. A solar storm is a regular, expected feature of our relationship with the star we orbit. An anti-satellite test is a political decision any of several governments could make this year, or next year, or any year. A software failure is an ordinary consequence of running complex systems at scale, and we run complex systems at scale every day. A bankruptcy is what happens to commercial enterprises when markets shift. Each of these triggers, considered individually, is plausible on a timescale of years. Considered collectively, the probability that none of them occurs over the next decade is low. Considered further in combination, the probability that some combination of them produces an overlapping disruption that exceeds the crash clock's 2.8-day window is not negligible. It may not be probable in any given year, but it is not negligible. And what makes this situation qualitatively different from other infrastructure fragilities is the absence of a safe failure mode. A terrestrial power grid can fail and be restored. A financial system can collapse and be rebuilt. A communications network can go offline and come back. These systems have restoration pathways. They have fallback states that, while uncomfortable, are survivable and recoverable. The orbital environment does not have a restoration pathway of that kind. Once a cascade is initiated and generates enough debris, the affected altitudes become unusable for timescales that are, for practical human purposes, permanent. There is no rebuild of the lost orbital volume. There is no restoration of the communications infrastructure that depended on it. There is no quick return to the previous state. What is lost, on the timescales of human generations rather than the timescales of human projects. The services that humanity currently receives from low Earth orbit are not optional luxuries at this point. Global navigation, which underpins logistics, aviation, precision agriculture, emergency services and financial timing networks, depends on satellite signals. Global communications, including the rapidly expanding satellite internet networks, depend on orbital infrastructure. Weather forecasting, which affects everything from airline routing to crop management to disaster response, depends on Earth observation satellites. Climate science, scientific research, intelligence gathering, disaster monitoring, maritime tracking, commercial imagery, and broadcast services all depend, to varying degrees, on satellite capability in low Earth orbit. The loss of significant portions of that capability would not be an inconvenience. It would be a systemic shock to terrestrial infrastructure that has quietly integrated space-based capability into almost every layer of modern logistics and communication. The existential framing here has to be handled carefully because the orbital environment does not directly threaten human survival the way, say, a pandemic or a nuclear exchange does. People would not die immediately from a Kessler cascade. The Earth would continue to be habitable. Civilization would continue to function. But the loss of low Earth orbit as a usable environment would be a civilizational setback of a kind we have no recent historical precedent for. It would take something humanity had come to depend on and remove it, not temporarily, but for timescales that exceed the planning horizons of any institution currently making decisions. It would, in a specific sense, close a frontier that we had only recently opened, and close it not through failure of ambition, but through failure of management. The unknown threshold behavior is the piece that should stay with you. We do not know, with any precision, how much more stress the current active management layer can sustain. before it starts failing in ways that produce visible cascade effects. We do not know whether the next coronal mass ejection will be a normal one or a Carrington scale one. We do not know when the next anti-satellite test will occur, or where or what debris cloud it will produce. We do not know which satellite constellation's financial backers will blink first. We do not know whether the next major software incident will be a minor embarrassment or a fleet-wide catastrophe. What we know is that the crash clock currently reads 2.8 days, and the house of cards is still standing, and the top is still spinning. What we do not know is what the reading will be next year, or the year after, or 10 years after that, if the current trajectories continue. The sky above your head tonight looks the same as it did when you were a kid. The Starlink trains glide across it in their strange bright chains. The satellites hum in their orbits. The conjunctions are resolved. The maneuvers fire. The house of cards stands. And every hour of every day, somewhere, people are working to keep it standing, because the alternative is a future where the sky we have taken for granted stops being available to us in the way we have assumed it always would be. The question we opened with was what it would take to push the orbital environment past the point where humanity can never go back. A single solar storm perhaps, a single anti-satellite test, a single software glitch, a single bankruptcy, a single bad weekend in which 2.8 days of margin turns out to be 2.8 days too few. We do not know which of those scenarios, if any, will be the one that tests the system. We know only that the system is being tested continuously, and that the test is getting harder every year, and that the clock that measures our margin is ticking down. Somewhere above your head, right now, a Starlink satellite is firing its thrusters. Somewhere, a tracking antenna is updating the orbit of a piece of debris. Somewhere, an algorithm is flagging a conjunction and routing it to an operator who has seconds to decide whether to act. Somewhere, the house of cards is shifting and hands are steadying it, and the top is still spinning and the sky is still quiet. For now, for 2.8 days, roughly, at a time. And the only question that really matters, the one we leave you with tonight, is whether, the next time the test comes, those 2.8 days will be enough. Sleep well.